This is the experimental determination of the relationship between pressure and the depth of an object submerged in water. This is our final project for ME348, Circuit Analysis, Instrumentation, and Statistics.
So, a quick overview of our video today. We're going to go through the engineering relevance, the hypothesis of the experiment, the experimental methodology, the data collection, the data analysis, and our results. Our team conducted an experiment exploring the correlation between pressure and the depth of water, a topic which is extensively covered in engineering courses like fluid mechanics and principles of turbomachinery. Understanding the pressure exerted by a fluid is crucial because of its influence on many factors, such as the flow rate and the fluid temperature in a system. This knowledge is particularly relevant in power generation using turbines and the manipulation of fluid flow characteristics with the compressors. The goal of this experiment is to establish a relationship between pressure and depth, providing valuable insights for enhancing the efficiency and design of specific systems. So, for our hypothesis, we aim to confirm that the pressure acting on a submerged object increases proportionally with the depth of the object. Drawing upon our knowledge of pressure and our engineering experiences, we anticipate that the pressure acting on a submerged object will increase as depth increases. Recognizing pressure as force per unit area, we acknowledge the gravitational force exerted by the column height of water above an object's cross-sectional area. To validate our hypothesis, we intend to measure water pressure on an object submerged to various depths in different containers with different shapes and sizes. By employing diverse containers, we aim to illustrate that pressure remains unaffected by fluid volumes and container shape. We predict that at greater depths, the pressure on the object will be higher due to the increased column height of water. The null hypothesis for this experiment is that pressure is independent of fluid depth and does not impact the pressure acting on a submerged object.
For our experiment, we used 4 different containers to fill with distilled water. Utilizing distilled water for this experiment eliminates the potential influence of impurities within the water to affect our circuitry, such as our pressure sensor connected to the Arduino. As you can see in the photo, one of the containers is a cylinder, one is a glass with curved sides, and another 2 are rectangles. This is to prove that it doesn't matter about the cross-sectional profile of the container or the volume. It is simply a function of depth within a given fluid that changes pressure. We also put markings on the side of each container to show what depth measurement we're at as we drop the pressure sensor into each container. A specialized Arduino-compatible sensor was purchased in order to collect absolute pressure readings at the marked depth in each container. The pressure sensor we acquired for this experiment is called the Adafruit BMP 390. This sensor could read both pressure and temperature, but in our experiment, we only pull the pressure readings from the sensor. We coated this in a special epoxy resin that would make the sensor water resistant as we dipped it into the distilled water to ensure that we could completely make the sensor water resistant during our testing. We also have the absolute pressure readings collected by this sensor to be displayed on an LCD screen that you could see here. The circuitry created to carry out the collection of this experimental data could be seen in this photo. The circuitry includes long lead wires that connect to the water-resistant pressure sensor to the Arduino. These long lead wires enabled us to dip the sensor into the depths of water without getting the Arduino or LCD screen or any other experimental hardware wet. Additionally, the circuit also has a potentiometer to adjust the contrast on the LCD screen so we could read clearly the pressure readings from the BMP sensor. To show off the Arduino code that we used to perform our data acquisition from the pressure sensor, we have basically 3 steps in which the code is doing. The first step is initializing the sensor and the LCD screen to the Arduino. The second step is just some basic setup things for the serial monitor and the LCD screen. And the third step is beginning the data acquisition from the pressure sensor and showcasing that onto the LCD screen. So you can see, especially in the data acquisition where a lot of the relevant lines of code are, we have it read from the BMP sensor the pressure, followed by underneath that we have the units for the pressure, and then we have this repeated code delayed every 1,000 milliseconds. So every second we're updating the pressure with what we're getting from the sensor.
To conduct the experiment, there were several absolute pressure measurements taken at various steps within each container. Because the containers were various shapes and sizes, some containers enabled the measurement of greater depths than others. For each container, the absolute pressure at each marked depth was recorded 3 separate times. Before each trial, the atmospheric pressure was recorded in order to calculate gauge pressure. The following equation was utilized to calculate gauge pressure. P gauge equals P absolute minus P atmospheric. On the left of the slide, you can see the pressure sensor measuring the pressure at a depth of 3 centimeters in the container with curved sides. In order to calculate the gauge pressure, the absolute pressure displayed on the LCD screen was subtracted from the atmospheric pressure taken at a depth of 0 centimeters. After conducting 3 trials at each depth, they were averaged and compared to a theoretical value, which was calculated using the equation rho g delta h. From there, a percent error was calculated in order to determine how far off the sensor was from the theoretical value. After that, the average gauge pressure versus depth for each container was plotted and a trend line was applied to each graph to determine a slope. The same plot of average gauge pressure versus depth for each container was created. These values were plotted and then a linear trend line was applied to each plot. The purpose of this was ultimately to compare it to the linear trend line created by the theoretical values. From here, we were able to make a comparison between the slopes of the linear trend line for each container and the linear trend line produced by the theoretical values in order to draw a conclusion for the experiment. This table shows the comparison of the slope of the linear trend line for each container shape against the theoretical slope. The theoretical slope is ultimately equal to the density of water multiplied by the gravitational constant. From here, we were able to compute a percent error for each trend line and recognize the difference. As you can see from the percent errors, they are very low, indicating that there is a high correlation between the depth of the submerged object and the pressure acting on the submerged object. In addition to comparing the slopes of the linear trend lines, we also collected all of the average gauge pressures at each depth within each container in order to calculate a global average gauge pressure for each depth. From there, we compared these global average gauge pressures to the theoretical gauge pressures calculated using the equation pressure equals density times gravity times the change in depth. As you can see from the data table, there is very low percent errors between the average gauge pressure and the theoretical gauge pressure. If you direct your attention to the plot at the bottom of the slide, you will notice that these lines nearly overlap when plotted, and they have a very similar slope. This indicates that the pressure sensor was very accurate in determining the pressure at each depth within the fluid. Based on the data analysis methods employed during this experiment, we were able to draw the conclusion that there is a high correlation between the pressure acting on a submerged object and the depth of that object submerged within the fluid. This ultimately proves our hypothesis to be correct. We noticed that there is a linear trend that is apparent across all of the containers. This signifies that pressure does not depend on container shape or the volume of fluid in the container, but rather just the depth of the submerged object within each container. We noticed that the slope of the linear trend lines applied to each plot of pressure versus depth for each container was very similar to the density of water multiplied by the gravitational constant. Overall, we have concluded that our hypothesis is correct. Some potential next steps in this experiment would be to repeat the experiment with fluids of different densities, such as oil. Additionally, we could also attempt the experiment with different types of fluids, such as compressible fluids and incompressible fluids, to see if they behave differently. Finally, we could completely change the experiment using the same sensor. We could change the temperature of air to see how it impacts the pressure in a fixed volume. This sort of experiment is associated with the ideal gas law, and because our sensor is able to measure both pressure and temperature, it would be applicable during this experiment. Thank you for watching.